file. Now we have explained the central limit theorem. We are going to use the central limit theorem to solve interesting questions about the random variables. Okay. Now you see the name of the question is normal approximation to binomial random variable. And let me tell you this, I mean, before solving this question, remember now, in the last part of yesterday's lecture, which is the last section of the 8th chapter, we have told that a binomial random variable is the sum of n independent and identically distributed Bernoulli random variables, right? So a binomial random variable is the sum of n independent and identically distributed Bernoulli random variables. So what happens if this size parameter goes to infinity? What happens if n goes to infinity? I mean, in that case, that binomial random variable would be approximately normal random variable, right? So because if you sum up n independent Bernoulli random variables, and if you sum up a sufficient number of them, these are independent, then their summation should be normally distributed according to the central limit theorem. And that summation is actually a binomial random variable, which means that binomial random variable will look alike a normal random variable. Now we are going to practice this. There are 336 seats in a theater hall, it says, and which holds the premiere of a movie. So there is a premiere, and for this premiere we are using basically a theater hall with 336 seats. For the premiere, 432 tickets are sold. Now people especially tend to sell more tickets than the available capacity. Why? Because they are counting on that each guest is likely to miss the premiere with 0.25 probability. So they are basically selling more tickets than the capacity, because they know that these kind of people who are invited to the premiere of a movie are likely to miss the premiere, okay, because they have another important thing to do. And that probability is independently equal to 0.25 for each invited guest. Now, what is the probability that a guest arrives and cannot find an empty seat? Okay, what does that mean? What is the probability that a guest arrives and cannot find an empty seat? That means at least 337 guests should come there, so we may experience this problem. If at least 337 guests come, then definitely at least one of the guests are going to one of the guests here is not going to be find an empty seat, right? Now, actually in this question, we are inviting 432 people, selling tickets to 432 people, and each of these 432 guests are likely to participate with 0.75 probability. And the total number of guests who are going to attend to the premiere is actually a binomial random variable if we assume independence between the behavior of the guests. So here x is a binomial random variable with size parameter 432, which is the total number of tickets sold, and success probability 0.75, which is the probability of each guest to attend. Now the desired probability is what? The probability of more than 336 guests to arrive, right? If the number of guests, x, to arrive or to attend to the premiere is greater than 336, then we are going to experience the problem that is described here. A guest will arrive and cannot find an empty seat. Now, for that probability, we need to sum up the probability mass values of the binomial distribution from 337 to 432. So if x is supposed to be greater than 336, this means from 337 to 432, we need to calculate the probabilities of x to be equal to each of these values and sum them up. because in all of these cases, we are going to experience that problem. Now, the probability mass function of the binomial random variable is size parameter, choose x, here x is I is changing from 337 to 432. We have n choose I times the success probability p to the power I times the failure probability 1 minus p to the power n minus I. So we need to sum up all of these probabilities. How many summations, how many components we need to calculate? I guess it is around 90, 95, right? So there are 95 components here we need to add up. And I mean, please try at home to calculate 432 to choose 337. Okay, so this number of combinations, 432 choose 337, is a very, very, very large number, my friends. Okay, so practically, you will not be able to calculate such a number of combinations. So remember, actually, I have asked a question in the midterm exam as well, if you have experienced it 3 hours ago. Now, remember now, in binomial distribution, if the size parameter is sufficiently large and the success probability is sufficiently small, then we can apply a Poisson approximation to the binomial random variable, if you remember. Okay? But here, unfortunately, the size parameter seems to be large enough, but the success probability is not small. So Poisson approximation is not a solution here. Poisson approximation requires the success probability to be small as well. Now, I cannot apply the Poisson approximation. I cannot calculate these probabilities because of this computational complexity. I mean, for example, 0.75 to the power 337. So let me calculate that value using a programming language. Okay. So what is 0.75 to the power 337? Now, can you see it? I don't know, but let me. So I suppose that you can see that 0.75 to the power 337 is a very, very, very small value. As you see, we have 10 to the power minus 43 here. So you need to write too many zeros after the decimal point. Then you can write the remaining value here. Okay. In fact, let me calculate 432 choose 337. And you see that value is a very, very large number. You need to write many zeros after writing this value. After that, you need to write many zeros. I mean, I suppose you cannot even read this value, right? I mean, which unit I'm going to use? Okay, million, billion. So what do we have after that? I don't know. So because of that reason, we will have a very large and very small value if you intend to calculate that probability. And when you multiply them, there will be always numerical errors. Okay. Now, I am going to calculate this probability how. But one thing that I know, which I have learned just half an hour ago, is the central limit theorem. Now, the central limit theorem tells me that the summation of a sufficiently large number of independent and identically distributed random variables should be behaving as a normal random variable. But what I know about binomial distribution is binomial random variable is the sum of n independent Bernoulli random variables. And here n is sufficiently large, I guess, 432. So what I am going to do is this. I cannot apply Poisson approximation. I cannot calculate the direct probability without using a computer. I can apply a central limit theorem since the binomial random variable is the sum of independent Bernoulli random variables, which are identical with success probability P. And since my size parameter 432 is sufficiently large, I'm not going to calculate that probability with a binomial random variable. So I'm not going to calculate that probability with a binomial random variable, but I am going to approximate that binomial random variable with a normal random variable, which has the same expected value as the binomial random variable and which has the same variance as the binomial random variable. Now, with this size parameter and the success probability, the expected value of x is going to be equal to n times p, which is 324. So the average of this binomial random variable is going to be 324, and the variance of that binomial random variable will be n times p times 1 minus p, which is going to be equal to 81. So if you plug in this 432 here and 0.75 and 0.25, you would get 81 as the variance. So what I am going to do is this. I am going to assume another normal random variable, which has the expected value equal to the expected value of this normal binomial random variable, and the standard deviation exactly equal to the standard deviation of that binomial random variable, which is 9. If the variance is equal to 81, then the standard deviation will be equal to 9. So I will assume that normal random variable, and I am going to answer the same question. I am going to answer the same question here with the normal random variable instead of the binomial one. However, there is one more thing that I need to tell you here. Now you see, x is an integer valued random variable, right? So this is a discrete. Binomial random variable is a discrete random variable. So when x is greater than 336, this means the least possible value for x is 337. And this is an integer valued random variable. Therefore, we will say that for any integer value x, we can do this approximation. So the probability of a binomial random variable to be equal to an integer value x can be approximated by the probability of the continuous normal random variable to be between minus plus 0.5 distant away from that value. Okay? So basically I'm going to explain this in Turkish again. Şimdi x kesikli bir asal değişken ya arkadaşlar. Discrete. Sadece tam sayı değerlerini alıyor. Ben diyelim ki x'in 336'ya eşit olma olasılığını hesaplamak istiyorum. Ama bu olasılığı, eşitlik olasılığını normal dağılımla yapacağım approximation'la hesaplamakta zorluk çekeceğim. Çünkü eşitlik olasılığı diye bir şey yok continuous rastsal değişkenlerde. Ne yapacağım peki bunu continuous rastsal değişkeni çevirirken? Madem sadece tam sayı değerleri alabiliyor bu x, normal rastsal değişken içinde bu tam sayı değerine artı eksi 0.5 ekleyeceğim ve diyeceğim ki 336'ya eşit olma olasılığı 335,5 ile 336,5 arasında normal rastsal değişkenin 335,5 ile 336,5 arasında olma olasılığına eşit olacak. So basically the probability of the discrete valued binomial random variable to be equal to exact an integer value is going to be approximated with a normal random variable which is continuous to be between 300 and 30, to be between 0.5 less than that value and 0.5 points greater than that value. For example, the probability of the binomial random variable to be equal to 336 will be approximated by the continuous normal random variable to be between 335.5 and 336.5. Okay? Now, because of that reason, if the original probability is asking me the binomial random variable to be greater than 336, now remember, this is a summation from 337 to 432. What I am going to do is this. I am going to take the value which is 0.5 less than 337, because you see in this inequality, 336 is not included. The first value that is included is 337. So I will take 0.5 less than 337, and I will say that what is the probability of the normal approximation of that binomial random variable to be more than 336.5. and which is going to be the probability of a standard normal random variable to be greater than the standardized value on the right-hand side. So remember now, we have approximated that binomial random variable with normal random variable location parameter 324 and scale parameter 9. So what I am going to do is this. I am going to subtract the location parameter from the both sides and divide the difference to the scale parameter, and the right-hand side will become 1.3889. So what I'm going to do is to calculate the probability of a standard normal random variable to be greater than this value, which is 1 minus the CDF at 1.3889. Now that CDF can be checked through the cumulative distribution function of the standard normal distribution, and that value would be 0.9176, and 1 minus that value will be 0.0824, and approximately with 0.0824 probability, there may be a problem for a guest when they come, they will not be able to find an empty seat. So this is just an approximate probability, not the exact one. Why? Because we are not using the original distribution. The original distribution is binomial. We are using the normal distribution, which is an approximate distribution, but the probability that we find with the original distribution is 0.081, which is very close to the approximate value that we have answered the question. Okay? Now let me show this thing to you. So this plot diagram here is the plot diagram for the probability mass function of the binomial distribution. So the binomial distribution with size parameter 432 and success probability 0.75, these are the probability mass values. For example, to this premiere, the probability of exactly 320 guests arriving is approximately 0.04, as you can see here. Okay, so that is the probability mass function, and the question is asking me what? The question is asking me the probability of the number of guests to be more than 337, which is the summation of the probability mass values of these red points. So starting from 337, 38, 39, 40, if the number of guests who will attend is larger than 336, then we will have a seating problem. So the question is asking me that probability, and that probability can be answered by a computer as 0.0810. Now, we have solved this question with a normal approximation. And in that normal approximation, we have said that instead of solving this problem with a discrete binomial random variable, I am going to assume that this binomial random variable can be approximated with a normal random variable with location parameter 324, which is the expected value of that binomial random variable. And the standard deviation is 9. The variance of the binomial random variable was 81. So we have used the expected value and the variance of the original distribution, the expected value and the variance of the original distribution to calculate the expected value and the variance and also the standard deviation of this normal approximation. And in that normal approximation, I have answered the same question as the tail probability at 336.5. So what is the probability that this approximate normal random variable to be more than or equal to 336.5? And that is the red area that I have calculated by standardization operation. And if you check out these two plot diagrams and these two continuous figure, the probabilities are approximately the same. The first one is 0.081, the second one is 0.082. Okay, so the probabilities are approximately the same. So, and you can easily see that the behavior of the normal distribution and the behavior of the discrete binomial random variable here, the probability mass function, they are almost looking like each other. The only thing is the binomial random variable is discrete valued, therefore it has a probability mass function, but the normal random variable is continuous valued, therefore it has a normal, continuous probability density function. So this is how we solve this question, my friends.